Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 2, Part B. Question 1 states, express the heat diffusion equation from Part A1 as an algebraic equation via Crank-Nicolson differencing. So the equation from Part A1 was dt is equal to alpha times the second derivative dt dx. Now what we also found was when we put that equation in algebraic form in part A, this is what it looked like. Oops. So get rid of one of those. Now what we want to do is turn this into the Crank-Nicolson equation, and to do that, we want to take the average of the approximation of the next time of the second derivative and the approximation of the second derivative at the current time. Now this is definitely all a little messed up. This is plus 1 equal to that. And so what we end up with when we take the average is tj n plus 1 is equal to tj n plus r times the approximation of the second derivative at the next time. So tj plus 1 at n plus 1 minus 2 tj n plus 1 minus tj plus 1 plus tj plus 1 n minus 2 n plus tj minus 1 n. All of that divided by 2. Now we are ready to move on to Part 2. This states, using von Neumann stability analysis, show that the Crank-Nicolson differencing scheme is stable regardless of the choice of R. If we head back over here and start analyzing this, if we remember from Part A, what we found was that this expression here is a solution to our derivative here. And ultimately, really, it's this sum down here. That's the true solution. But we picked one particular term to look at just to make things a little bit more simple. And what we ended up with was this here. And from there, we were able to prove that for part A, R needed to be less than or equal to 1/2. We could use something similar here for the Crank-Nicolson equation. So if we take this expression and do kind of the same thing for the equation we have above, what we end up with is tj n plus 1 is equal to tj n plus. The other thing that we want to do before we go too much farther is take this 2 and lump it in with our r value just to make writing things down a little bit simpler. And so what we end up with is r times e I k x times tj n plus 1 minus 2 times tj n plus 1 plus e negative I k delta x times tj n plus 1 plus e I k delta x times tjn minus 2 tjn plus e to the negative ik delta x times tj n. Now what we want to do is separate our tjn plus 1 and our tjn terms. So we're going to put our tjn plus 1 terms on the left-hand side of the equation and our tjn terms on the right-hand side of the equation. And do that, we end up with tjn plus 1. And since there's a tjn plus 1 term on all of these, what we can do is factor that out. We end up with 1 minus r times e to the ik delta x plus e to the negative ik delta x minus 2 is equal to tjn. If we do the same thing on this side, we end up with 1 plus r e to the ik delta x plus e to the negative ik delta x minus 2. Now, like in part A, we know that this term here ends up being a cosine term. So if we put that in, we end up with tj plus 1 times 1 minus r times 2 cosine k delta x minus 2 equal to tj n times 1 plus r times 2 cosine k delta x minus 2. Now we're going to factor out a negative 2 from the 2 cosine minus 2 terms, leaving us with tj n plus 1 is 1 plus 2r times 1 minus cosine k delta x is equal to tjn times 1 minus 2r times 1 minus cosine k delta x. Now if we want to get tjn plus 1 by itself on the left-hand side of the equation, we divide across by this big long term there. We end up with tjn plus 1 is equal to tjn times 1 minus 2r 1 minus cosine delta x divided by 1 plus 2r times 1 minus cosine k delta x. And here we now have 2 of these 2r 1 minus cosine terms, so we can just assign that some variable that we call z. When we do that, we end up with tj plus 1 to tj n times 1 minus z over 1 plus z. Now if we look a little bit farther into this z term, we know that the largest value that cosine can be is 1, which would give us a 1 minus 1 to 0. So the largest value that z could be is 0. So z is always greater than or equal to 0. This is important because it means that our value is always going to be positive, and when we come down farther to this term, we know that the numerator is always going to be smaller than the denominator, and this means that the value can't blow up and go to infinity in this scenario, allowing us to pick any value of r that we want. Finally, we can move on to question 3. This states simulate the time-dependent response of a uniform bar initially at 20 degrees Celsius after its ends are raised, then maintained at 50 and 80 degrees Celsius respectively. Discretize the bar with 100 time-dependent temperatures and solve the equation from part 1 using scipy.linalg.solve banded for r is equal to 2 over 2500 time steps. Plot the simulated results in 100 time step intervals. So before we go over to Google Colab and start coding this, we really want to make sure we understand what we're trying to do. So in the previous part, we found this equation right here. Just move that over here for reference. And just like before, we do want to keep that 2 lumped in with the r. But now we want to move our knowns and our unknowns onto opposite sides. So we're going to put our TJN plus 1s on the left-hand side of the equation and our TJNs on the right-hand side of the equation. So what we end up with is negative r tj minus 1 n plus 1 plus 2r 2r plus 1 tj n plus 1 minus r times tj plus 1 n plus 1 is equal to r times tj minus 1 n plus 2r minus 1 tj n plus r times tj plus 1 times n. Now to do this for 100 temperatures or many temperatures, however many you want really, you're going to have a lot of terms, you're going to have a lot of unknowns, so the best way to solve for this is to put this into matrix form. So to start, we're going to have our matrix of positions, J1, J2, J3, all the way down. And then we have our vector of temperatures. We have T1, T2, T3, all the way down. And these are T as n plus 1. And for these, we do have 2 knowns. We know that our T left is equal to 50, and our T right is equal to 80 degrees. And what we're going to end up with is a bunch of values. To really start setting up this matrix, we're going to look at j is equal to 2 first. So for j is equal to 2, we know that looking at our equation that our temperatures only depend on the position that you're looking at. That's this TJ here. The temperature that at the position to your left, TJ minus 1, and your position to your right, TJ plus 1. So when you're going through your matrix, we're looking at T1 first. And for j equals 2, that is our j minus 1 here, right? So that would be negative r. And then for T2, that's Tj for this one, because our j is 2, which means that we have a 2r plus 1. And then for Tj plus 1, that's our T3, which we have right there, and that's going to be minus 1 as well. But when you move on to T4, T4, T5, T6, T whatever, that's no longer part of our equation, so all of those would end up being 0. So if we do the same thing for J3, what we'll find is that T1 is going to be 0 because at position 3, we're only dependent on positions 2 and 4. Right? So now we have a 0, but at T2, that's our Tj minus 1, so we have a negative 1, or negative r. At T3, that's our Tj, so we end up with 2r plus 1. And then finally at T4, that's our Tj plus 1. We have a negative r. And then my matrix just isn't big enough, but there would be a whole bunch of zeros. So now we can go ahead and fill out this right-hand side of the equation for each of those. So what we'd end up with is r times t for j minus 1 plus 2r minus 1 times t2 plus r times t3, which would be tn's for all of those. And then similarly for j equals 3, you would have r times t2n plus 2r minus 1 times t3n plus r times t4n. Right. Now you would repeat this process for all the positions that you have set for the matrix, but we have two special positions, and that's our very first one at j equals 1 and our very last one. And this is because if you look at the matrix, so we have at t equals 1, that's our tj, right? So you have 2r plus 1 here, and then t2 is our tj plus 1, which would give us a negative r, but then it would go on to t3, 4, 5, and we're not dependent on that for j equals 1, but we still have to look at the temperature to the left, over here, for this position, but this is a known and not an unknown, right? We know that our TL is equal to 50. So what we would want to do is get that put on the other side of the equation, so we would do, we would just add it to both sides, right? So what you end up with is 2TL plus 2r minus 1 T1n plus r times T2n, right? Because we already knew it in the first place, and then we added another TL. There should be an r in there. Right. Now for the last one, we do something similar, and my matrix isn't super well drawn, but we know that this last position here, you're going to have your 2r plus 1, the position that you're at, because your diagonal would follow this if I'd drawn it a little bit better. And then you have to look to the left and to the right, right? So to the left, you would have your previous temperature, your Tj minus 1, and have a negative r here. And if you look to your right, just like for the first position, we have a known there. We have our Tr. So what you end up for this one is you have your r times Tj minus 1 plus your 2r minus 1 Tj plus r times plus 2r times Tr. And there you have your matrix, And just to draw it out a little better, what you're really going to end up with for this one over here is you're going to have some diagonals. 2r plus 1 is 2r plus 1. Enough. And then you have your negative r values under here and up here. And then everything else you would fill in with zeros. So you have a sparse matrix. Then, now that we have that set up, we can go ahead and use the tools provided by Python to evaluate this and actually plot it. Moving over to Google Colab, I made a copy of the code that we wrote in Part A. And now we're just going to edit it to make it work for what we want to do in Part B. First thing we want to do is import another library that we're going to need. So we want to import from scipy.winout import solve underscore bandit. Perfect. Now we want to change this R value to 2. We change the names of these to T left and T right. Now we just set up our matrix. So for our upper and lower diagonals, we have np dot full, and those are just negative r. And then our middle diagonal is np dot full, and it's 1 plus 2 times r. And to put it all together, we do sparse underscore a is equal to np dot c. I'm gonna just concatenate those together. So we have our upper and lower diagonals. And then we have our middle diagonal. And then we're going to transpose that to make sure that it's the correct size when we're multiplying. Now down here we just have a couple minor edits. We're going to do plus 2s because we have the 100 slices plus RT left and RT right. For our y, when we plot, we're going to have p dot row. We have our t right, t, and t left. So again, that's just adding on our known temperatures. We need that there, and we need it here. And this time we want to go from 1 to 2500 with 100 steps. Now we need to get rid of this here, and what we want to put in its place is our right-hand side of the equation. We're going to call b. So there we have 1 minus 2 times r. And all of this here we're just getting from that matrix that we just set up. So this is t. And then from 1 to -1, so these are just our middle values. We're going to add on to r times the temperatures to the right. So that's our second one all the way through to the end. And we also need to add on our temperature to the left, so r times t, that very first one, through to the second to last value. Now, if you remember, our first and last values are special. So for those, what we want to do is do R times that first temperature value plus our temperature to the left. So 2 times R times T left. And for our last one, we're going to add on our last value, last unknown temperature value, plus 2 times R times T right. Oops. That should be to the left right there. And then finally we're going to put it all together. T equal to solve underscore abandon. We have one upper and one lower diagonal. We have our sparse underscore A. So our values for the matrix, and then we have our right-hand side of the equation. Fingers crossed that it works. And there we go. We can see our plot of temperatures. It's pretty much what we expect, and it looks very similar to what we saw in Part A.